All right, so this problem, it's really amazing that even revisiting this problem after almost 2 years, it's still giving me trouble. And there's just a lot there's just a lot to consider here. And the question that they're asking us is which line angle drawing best represents the Newman projection shown below. So my strategy for this is to first rotate the Newman projection into something that is going to work just a little bit easier for me. And the way I did that was I literally took a screenshot and rotated the entire compound here where that my methyl groups are going north and south. And I want the methyl group on this front carbon. And remember, this carbon of a Newman projection is, we're looking at it head on. And the second carbon is eclipsed behind it. Obviously, the sizes aren't that big of a difference when you're actually looking at the model, but this in the Newman projection, that's how they're showing that. So literally all I did was rotate. If you envision like a captain's wheel and I'm rotating these three spokes, I'm bringing this methyl group either 2 positions up or I'm just bringing it one direction to the left. And I can see that if I'm going clockwise from the methyl group to the hydrogen, and I go clockwise here from the methyl group, I still hit the hydrogen. So I'm just putting it in a nicer way for me to look at. It's going to make it easier for me to transpose this Newman projection into a perspective drawing, all right? So I did the same thing with the back carbon here, and you can see that my hydrogens are still on the same side of this compound, and the chlorines are still on the same side also. So I really haven't rotated any bonds. I just rotated this entire compound and kind of kept everything. We're still going CH3, HH, CH3, CH3, HH, CH3, Cl, Cl. All right, so we need to pick a direction to look at this because when we're looking at a perspective drawing, we're looking at it from, looking dead on this line here instead of with a Newman projection where we're looking at it from this direction. So we need to pick, do we want to look from this side or from this side? Now, because I want this front carbon to be the first carbon of these perspective drawings, I want to look from the right here because I want the methyl group of this first carbon to be pointed upwards. And that's exactly what I did with this perspective drawing here. So I transpose now this blue to this blue here. So I have this methyl group pointing upward, and you always want to keep that clean syntax of keeping your methyl groups locked in line in this kind of chair. It's not a chair, but, comparing it to a real chair, not a chemistry chair formation here, okay? And if we're looking at it from this direction, we see that this hydrogen is definitely coming in our direction. So what does that mean? Well, it means a hydrogen is going to be in a solid wedge, which it absolutely is. And if we're looking from this direction, we can see the chlorine is going away from us, and that's why I put it on the hatched wedge. So in terms of syntax in the book or here on the practice exam, you're always going to see this group written this way, where you have that hatched wedge above the solid wedge. All right, you're always going to see that, luckily. It's this side that is going to give us some problems because it's drawn differently here than it is drawn in the book. In the book, it's drawn where this hatched wedge is always above the solid wedge. So that definitely is very confusing for a student. So let's look at how we would draw this back carbon. Again, we're looking from this direction, and our methyl group is going down here. So that's why I've locked it into this position. Now, we know the hydrogen is definitely coming in our direction, so the hydrogen is going to be on a solid wedge. But the question is, do we put the solid wedge above the hatched wedge like we do in all of these examples, or do we put the solid wedge below and keep the hatched wedge above like we see in the book? Now, it turns out for this example, it actually doesn't matter because if you do the RNS configuration for both of these, and to do that, you realize that, well, the hydrogen is not on a hatched wedge for either example, so we need to make a swap. So if we want to do our priorities, hydrogen always gets the fourth, methyl almost always gets the third, and we're now comparing this chlorine group, which immediately we're hitting a hydrogen. This is a dead giveaway that this is a 1. And our other group here is we're hitting a carbon first. There's really no need to go to all these other substituents. However, we do know that this carbon, because we're hitting a chlorine here, and because this carbon, we're hitting hydrogens here, that this is going to be a priority, and this is going to get the number 2, okay? So knowing that we have to make that switch, we can simply just make hydrogen the number 1, make chlorine the number 4, because you're switching your hydrogen with whatever is sitting on the hatched wedge. And if we go from 1 to 2 to 3, we know that we're going to the left, which would be S, but since we had to make a switch, this is in the R configuration. Now, if I draw this the other way, I do the same exact thing where, yeah, I still need to switch my chlorine and my hydrogen, so I'm making an interchange. But if I go from my 1 to my 2 to my 3, I'm also going to the left, which would be S, but knowing I had to do an interchange, this would be an R. So it doesn't matter how you draw this. But now what we can easily do, because our test writer has very politely given us answers A and B in this nice, clean, inline methyl, alkyl formation, is we should be able to compare what we just drew to A and B rather easily. So let's see what we can figure out. So if we're looking at these from the side, and we say, well, this is our first one, and this is our second one, well, all right, well, what do we see here? So we see a chlorine coming towards us and a hydrogen coming towards us. However, keep in mind, we can rotate these groups, okay? We can rotate these groups. However, the hydrogens, as we saw that they're on the same side up here and the same side over here, always, if we're locking in our methyl groups, always have to be going in the same direction. Sure, we could bring this methyl group up here. We could rotate this bond, but then we really can no longer compare the two. So just the fact that we see chlorine and a hydrogen coming towards us with the methyl groups in line, we know that that's impossible. These cannot be the same exact compounds, right? So I'm going to X out A. Now, for the sake of knowing our RNS configuration, we might as well bang out the RNS configuration for our group, our blue group here. So again, methyl gets the third, chlorine as a halogen gets the first, hydrogen gets the fourth, and this group over here gets the second. We do need to make an interchange here because hydrogen is not on the hatched wedge. So we're going to give this a 1, and we're going to give this one a 4. And then we can draw our arrow. And our arrow is going to go from 1 to 2 to 3. That's going to the left, which is going to be S. But then knowing we had to make an interchange, we know this is going to be R. So if we wanted to double check ourselves real quick, you really need to learn how to do these RNS configurations really quickly. Now, we don't need to make any changes here because we see hydrogen is on a hatched wedge. So we can go from 1 to 2 to 3. We know we're going to the left. That is going to be an S formation. So we no longer actually need to focus on A, but just for the heck of it, let's do the same thing on this side. We do need to make a switch here with 1 and 4. So this is going to be 1, 2, 3. We're going to the left. This is S. So this side is indeed going to be R. So half of this compound is correct, but the other isn't. And we can actually very clearly see that this side is correct because it's exactly the same as what we drew. It's a methyl group in line, it's a hydrogen on a solid wedge, and it's a chlorine on a hatched wedge. So half of this is actually correct, which is interesting, kind of interesting to note. But this side is not correct, so we can move on to B, all right? Now, B is very interesting because look at this. The methyl groups are in line, which is what we want, and both chlorines are coming towards us, okay? Now, in our model here, our hydrogens are coming towards us, our chlorines are going away from us. But if we rotated our model, couldn't you say that our chlorines are then coming towards us and our hydrogens are going away from us? Well, you could do that, but then our methyl groups would kind of be slightly in different directions. They wouldn't really be locked in. So rather than, kind of finagle that, we could just simply do the R and S for this. So the one on the left is going to be pretty easy. And actually, it's the same exact setup as what we see above. So we actually know this is S, and we know that this is incorrect already, right? These are the same. We already did our R and S configuration, so we know this is S. But just for the heck of it, let's see the configuration of the side on the right here. So we don't have to do an interchange because hydrogen is on a hatched wedge. So we can go 1, 2, 3, left, which will be S. So this is going to be SS. And we're looking for RR. So this would actually be the enantiomer. This is actually the enantiomer of what we're looking for. This here would be a diastereomer. Okay. All right. So let's kind of keep moving. So now, unfortunately, we can't really use our locked-in methyl strategy. We're kind of losing that a little bit here. So really the easiest way to do this is just to keep going with R and S. We see a nice hydrogen that's on a hatched wedge. That's awesome. So we'll do 1, 2, 3. We're going to the right. So this is going to be R. So that's awesome. Half of this compound is right. And before we move forward and do the R and S on the other side there, can we easily compare this and this? Are these truly the same thing? I want you to visualize for a second this methyl group coming towards us, right? Grab this methyl group and pull it up towards us. We're going to push it north. We're going to push it up so that it's in this inline position. Visualize, and if you can master rotating a molecule like this in your mind and on paper, you will be so great at this course. What is going to happen to these two molecules if we push this methyl group up here? Well, it's kind of like the spokes of a fan. This chlorine is going to go down, and it's going to go down, and it's going to be in a wedged position like this. The hydrogen, as we pull this methyl group up, the hydrogen is going to take the place of that hatched wedge and is going to be coming towards us. And you can see that's exactly the configuration we have up here. So it's really a beautiful thing if you can truly understand that, all right? So let's look over at this side here. And let's do that visualization again real quick. Let's pull this methyl group towards us to this inline position. Okay, the hydrogen is going to be pushed upward because we're pulling the methyl group towards us, and this chlorine is then going to be in the back here. Okay, so what's interesting is we just made an exact match of what we had over here by doing that visualization. Let's do it a second way. If you're not great at the visualization, let's just do the R and the S here. I'll write them out for you. Hydrogen's going to be 4, methyl's going to be 3, chlorine's going to be 1, this is going to be 2. Do we need to make an interchange? Yes, we do. We need to switch this group and this group. So we're going to put our 3 here, and we're going to put our 4 here, and then we can draw our arrow from 1 to 2 to 3. We're going to the left, which is S, but we made an interchange, so we know this is going to be R. So there you go. This is the identical compound to what we're looking for, okay? This we ruled out. But let's rule out D. Let's make sure we really understand what's happening here. D is really interesting because our methyl groups are not in our inline position. However, they're paired up. They're both in a hatched wedge type of position. So if we picked that model up and kind of turned it on its head, it kind of would be where we want it to be. So again, you can do this in 2 different ways. Let's say we don't want to do R and S. We have to do 2 interchanges here because the hydrogens are not where we want them. Let's see if we can redraw this compound. So, okay, let's see. If we want to put this methyl group up here, we want to pull the chlorine down. And if we pull the chlorine down, that's going to go here, and the methyl group will go up. And the only other option is for that hydrogen group, we have now pushed back, okay? Now, if we want to pull this methyl group towards us, it's going to push the hydrogen upward here, and it's going to push that chlorine. It's going to push that chlorine back there. So that's a really quick reorganization of what we did. However, we can see that with our methyl groups in line, we have a chlorine coming towards us and a hydrogen coming towards us. We know that can't be the case. We know that we need both hydrogens on the same side or both chlorines on the same side. So we know that those aren't going to be identical compounds. So, and we could double that up. We kind of did C and D in two different ways. But I'm going to leave that to you. If you want to practice with C in that kind of visual rotation strategy, or if you want to sign the R and S for D, and you can see that you're not going to be getting the same answer. You would get a diastereomer. I believe I would have to do the R and S on that. All right, let's just do it real quick. So we do have to make an interchange here. We have a 1, we have a 4, we have a 3, we have a 2. We need to interchange this, and we're going to go 1, 2, 3, R, but we made an interchange, so that's going to be S. It's going to be S. And then on this side here, we have 4, 3, 1, 2. We do need to make an interchange here between 4 and 3. So this will be 3. This will be 4. Drawing our arrow, we have 1, 2, 3, left S. Since we made an interchange, this will be R. So SR. So yeah, that's going to be a diastereomer down here as well. So that's it. So that is how to solve this problem. Using a model would be much quicker than this, but this is how you would want to do this if you're using the R&S system and this kind of visual, rotation of all these compounds.